Have you ever wondered why a drop of ink disperses in water but never gathers itself back into a drop? Or why a ball rolls down a hill but never up? In the thermodynamics of the universe, this downhill direction is governed by spontaneity. Look at the energy landscape on your screen. The ball represents a chemical system. It doesn't need a push. Gravity, or in chemistry, Gibbs free energy, pulls it from a state of high instability to stability. We can predict if a reaction happens simply by asking, is there a valley below us?
Predicting the future of a reaction isn't just about energy dropping, it's a negotiation. Imagine a cosmic scale. On the left, we have enthalpy, the desire to release heat and bond tightly. On the right, entropy, the desire for freedom and chaos. Gibbs free energy is the referee. Watch as we increase the temperature. The chaos side gets heavier, tipping the scale. A reaction that is impossible at room temperature might suddenly become spontaneous if we just add enough heat to let entropy win.
When a system reaches equilibrium, it looks like it has stopped. But zoom in. It is not a frozen statue. It is a frantic exchange. Imagine two rooms with people running back and forth. Equilibrium is simply the moment when the number of people entering the room equals the number leaving. Visually, watch the particles exchange. The net change is zero, but the movement never ceases. We predict this state when the forward rate matches the reverse rate perfectly.
How do we know which way the reaction will go right now? Think of it like a GPS. K is our destination, the equilibrium constant, a fixed point on the map defined by nature. Q is our current location. Look at the gauge. If Q is less than K, the needle is to the left, and the system must drive forward to reach the target. If Q is greater, we've overshot, and nature will force the reaction into reverse. We calculate Q to predict the immediate future.
Finally, what happens if we poke the bear? Le Chatelier's principle teaches us that if we stress a system at equilibrium by squeezing it, heating it, or adding matter, it doesn't just break, it fights back. Visualize a piston filled with gas. As I compress it, slide 0.3, the pressure spikes. The system responds by reacting to reduce the number of gas molecules, effectively lowering the pressure back down. We can predict exactly how the system will dodge the punch to regain balance.